Hello everyone, this is Introduction to Computer Communication Network Systems. We are presenting our final project based on this course. Our project topic is Wireless Network Simulation and Performance Enhancement based on Bianchi's Wi-Fi network model. I am Prathamesh and my colleagues Leah, Atika and Naimisha will be presenting this brief presentation along with some critical findings. The objectives of this project. This project 4 improves upon the simulation program from the projects 2 and 3. Additionally, it makes the code more flexible and efficient. Certain parameters have been added to the code. Features to be added include a distribution of Wi-Fi nodes based on maximum distance, configurable packet size and interval, packet rate simulation, and customizable RTS-CTS threshold parameters. More parameters along with this can be added to the command line. Additionally, the nodes to be arranged are arranged in random, circular, or spiral patterns. The interference factor to be calculated to measure the impact of multiple stations transmitting data at the same time, as interference can cause reduced throughput, increased latency, decreased reliability and decreased capacity. Now, why simulation? Wireless networks are critical for our day-to-day life and the demand is constantly increasing. This simulation is an approach to improve the wireless network performance at a reduced cost. Some tasks that we did in this final project include adding new capabilities, increasing the flexibility of the existing code. Upgraded code includes the customizable features. The nodes are arranged arbitrarily, symmetrically, or spirally for better performance. Who will be benefited? Researchers, network managers, and others who aim to boost the performance of wireless networks can benefit from this code.
For the implementation of our project, the first thing we did was to fix the Wi-Fi node distribution. The code was improved to arrange the Wi-Fi nodes in random, circle, and spiral distribution. A new command line argument called Enhancement is included in the code to distribute the Wi-Fi stations based on the max distance argument initialized by the user. Here, the distance between each station is computed by max distance divided by number of Wi-Fi stations. The program has 3 options for node arrangement determined by the arrangement command line argument: random, circle, and spiral. The arrangement argument determines how the nodes are positioned within the range specified by the max distance argument. The nodes are arranged in a pattern within the max distance range. The default arrangement is always circle. Based on the value given for the arrangement in command line, the nodes will be arranged. So for arrangement equal to random, the pattern looks like this. For arrangement equals to circle, the pattern looks like this. And when the arrangement is a spiral, the pattern looks like this. After this, the code had 2 new command line options: packet size and interval. These options allow users to set the size of the packets to be transmitted and the interval at which the packets are delivered. This feature allows for uniform configuration of packet size and interval for all network nodes. User can adjust these options to meet their specific needs, providing greater flexibility and control over network behavior. And improvements have been made to the program, especially to enable simulation of the network using packet rate. To facilitate this simulation, a new parameter called isSimulation based on packet rate has been added to the program. In order to utilize this feature, users are required to set the value of isSimulation based on packet rate to true.
Coming to implementation packet rate calculation, once the parameters are enabled, users must provide the packet rate and packet size to simulate the network. The interval between packets is then calculated based on the bandwidth of the network, the packet size, the number of Wi-Fi stations, and the packet rate using the equation shown below. configurable RTS-CTS threshold. The RTS-CTS threshold parameter has been made customizable through a command line argument to provide users more control over the network simulations. This improvement gives users the ability to change the RTS-CTS threshold value to suit their unique simulation needs. Result. This is a screenshot of our simulation getting built. So here we can see the number of Wi-Fi stations that we have taken is 10. The RTS-CTS threshold is 800, packet size of 1400, duration of 100 seconds, maximum distance of 20, and the arrangement is circle. Also, the 10 nodes along with their position is visible, and the TX packets, RX packets along with their ratio can be seen. Major impact factors affecting Wi-Fi communication. There are many factors that affect the performance of Wi-Fi network. Some of them include distance, station density, packet size, interference, obstructions, bandwidth, and so on. Overall, a Wi-Fi network's performance is defined by a mix of these elements. Each of them can be optimized to increase Wi-Fi communication dependability and speed. On the first graph, we can see the impact of the distance. The impact of the distance with respect to the performance of the networks is evaluated here. As the distance increases, the throughput of the network decreases and vice versa. Similarly, as the distance increases, it is also noted that the TX packets and RX packets decreases. Effect of interference. Yes, the stations in the Wi-Fi Bianchi simulation can interfere with each other as they share the same wireless channel. These effects of interference can include reduced throughput. Interference can cause collisions and retransmission, which reduces the overall throughput of the network. Increased latency. Interference can cause delay in packets transmission and reception, increasing the latency of the network. And decrease reliability. Interference can cause packet loss and corruption, reducing the reliability of the network. Decrease capacity. Interference reduces the overall capacity of the channel by decreasing the number of successful transmissions that can occur in the given time. The interference factor is calculated by using the formula shown below. As shown in the graph, we can see as the interference factor increases, the network performance deteriorates with lower packet delivery ratio, lower throughput, and higher latency.
The effect of RTS-CTS threshold. The request to send RTS and the clear to send CTS signals are used for the flow control in a wireless network below a certain size of data packet, which is determined by the RTS-CTS threshold constant. RTS-CTS is used to prevent data collisions if the packet size is more than the threshold value, and if the packet size is lesser than the RTS-CTS threshold, the mechanism will not be triggered. If the wireless channel is open and no other nodes are transmitting, the transmitter will send the data without asking the receiver's consent. Hence, RTS-CTS flow control may not be of much use to the stations transmitting smaller packets. If the packet size is equal to the RTS-CTS threshold, the RTS-CTS mechanism will behave differently depending upon the individual implementation of the Wi-Fi device and the network settings. The mechanism will not be as effective and performant as it could be. If the packet size is greater than the RTS-CTS threshold, this is where the RTS-CTS is most effective. This is due to the longer transmission times and longer wireless medium usage caused by larger packets, which raise the risk of data collisions. Using RTS-CTS, the receiving data station responds with a clear to send signal after transmitting station has asked for the permission to send data. This flow management technique makes sure that there aren't two or more stations using the wireless medium at once, which lowers the chances of collisions and boosts the overall performance. In order to analyze the impact of the RTS-CTS threshold, we have used a parameter named packet loss rate, which is computed using the given equation. The parameters for this factor is the number of packets the node received and the packets it's been transferred. Factor, the packet loss rate, will help us to understand the effect of the RTS-CTS threshold. The graph shown in the given slide illustrates that there is a clear relationship between the packet size, packet loss rate, and throughput. The packet loss rate is a direct reflection of the impact of the RTS-CTS threshold. As the packet size increases, the packet loss rate also increases while throughput decreases with high availability. However, upon the activation of the RTS-CTS threshold, there is a noticeable improvement in the stability of packet loss and throughput. This indicates that the RTS-CTS threshold is effective in mitigating the negative effects of the increasing packet size on the network performance. The impact of the distance. The impact of the distance with respect to the performance of the network is evaluated here. Around 30 nodes were distributed spirally with a maximum distance of 30 meters. From the simulations, it was observed that the Wi-Fi performance and the distance holds an inverse relationship between them. As the distance increases, the throughput of the network decreases and vice versa. Similarly, as the distance increases, it's also noted that the TX packet rate and the RX packets also decreases. Impact of the density. To evaluate the impact of density on the network, multiple simulations were conducted at the same maximum distance from the standard Wi-Fi nodes. Each simulation iteration increased the number of stations to progressively increase the node density within the network. The nodes were distributed randomly to ensure a fair and unbiased evaluation. A few observations that were noted are, as the density increases, the performance of the network degrades. The density and the network performance holds an inverse proportional relationship. As the density increases, throughput decreases. When too many devices are connected to a Wi-Fi access point, it can cause congestion and slow down the connection and speed up for all the devices. This is because each device is competing for the same limited bandwidth and network resources. The density was calculated using the equation given in the slide. Impact of the packet size. Smaller packet sizes can contribute to faster transmission times and lower latency, but they can also cause increased overhead and poor throughput. This is so that the additional header and other console information may be included in each smaller packet, which can limit the amount of valuable data that can be transmitted in a given length of time. On the other hand, by lowering the amount of overhead per unit of data, higher packet size can boost the throughput. Larger packets, however, may also result in longer waiting times, greater latency, and a high chance of packet loss and retransmissions. As per the figure shown in this slide, here the RTS threshold is 800. As the packet size increases, the throughput increases, but on the second half, one could see that the throughput decreases as the packet size increases. So, in order to have the best transmission, a balance needs to be maintained. The packet size shouldn't be too small or shouldn't be too large. This project has described the modifications made to the code from Project 3, which included additional configurations to enhance flexibility. The modification included changes to the distribution of the Wi-Fi nodes, configurable packet size, interval, packet rate, and RTS-CTS threshold. The project also addresses the questions regarding the impact of the interference in the Wi-Fi network, the impact of the distance, impact of the density of the network, the impact of packet size in the network, and also the impact of the RTS-CTS threshold. The project has been run in multiple simulations in order to demonstrate the effects of each of the components that's been asked as part of the project 4. Thank you.